Plate tectonics. Sorry, but this is kind of a big topic. I'm not sure how long it's going to take me to get through this, but it's an important one that is well covered on the test. So let's go. All right. So the first thing we need to know in order to understand plate tectonics is a concept called convection. It's something we'll see again this year. So convection basically is the upward movement of hot material and the downward movement of cold material in a fluid. So in a solid or a gas, or I'm sorry, a liquid or a gas. In the case of the Earth, we're talking about a liquid. So just as like when you heat water, the hot water goes up and the cold water sinks. Or if you make a fire, you might notice that the smoke moves up and then it cools off and it sinks. Those are examples of convection. Well, it turns out convection happens for this reason. When material is hot, the atoms shake more violently, they get farther apart, they become less dense, and fluids that are less dense float in things that are more dense. So, hot material, gas or liquid, is going to float upwards, and then as it does, it's going to cool off, and as it cools off, it's going to sink back down to the heating source. And so, you're going to get this circular movement called a convection current or a convection cell. And this, it turns out, is what drives the changes in the surface of the Earth, a process we call plate tectonics. These convection currents happen in different parts of it, but the place we're most concerned with in this topic is within the mantle. So the idea is the mantle is this semi-liquid material. When we said you could think of it almost like uh, like like clay or Play-Doh, if you know what that is, or thick cement. But basically, it's capable of movement, but not like a liquid. But it flows. And the idea is that there are places in the Earth's outer core, for whatever reason, we're still not quite sure, are hotter than others. And then what happens is we get these plumes, these upward movements of convection over these areas of particular heat. And so what happens is hot material moves upwards, it cools off, and then it sinks back down into the lower mantle. And this process is going on all over the world. These convection cells, it turns out, they drag the crust of the Earth with them. So as these convection currents in the mantle move across their sort of the top of their path, they drag the lithosphere with them and cause it to be set in motion, albeit slowly. But that's what changes the arrangement of the continents at the surface of the Earth. So let's just sort of dive into this a little bit. So where these convection currents reach the surface, they have a tendency to cause a break or a crack in the surface. There's a thinning, and there's basically a pulling apart of the Earth's surface at that point. So, part of it's trying to move one way, and part of it's trying to move the other way. And where it breaks, we get this region we call a spreading center. And what will happen is material will come up here as liquid lava, and it will freeze into place as rock, known as basalt, which is what the seafloor is made out of. So the seafloor, as I said earlier, is made out of similar material to the mantle. This is slightly different in composition, but basically the driving force behind plate tectonics is this moving apart of the surface of the Earth as mantle material comes up and takes its place. Now, we often call this a divergent boundary because these two pieces of the Earth are diverging from each other. So these spreading centers, as they're referred to, can be seen all over the Earth, and they generally take two forms. Well, three if we include a particular one of Iceland. But basically, they're called the mid-ocean ridges. So if you look at Google Maps or any map that shows the underwater features of the world, you'll notice that there are these mountain ranges with this crack in the middle. And there's a lot of volcanic activity all along these cracks. Perhaps you've heard of like vent life. I think we mentioned it earlier in the year when we were talking about how most life on Earth is solar powered. But the places that aren't are along these ridges, these mid-ocean ridges, and we see them all over the planet. And interestingly, if we sample the rocks here, we find them to be quite young. Like they're not that old, geologically speaking. Whereas as we move away from them, it gets older and older and older. So what it tells us is new material is being added here and it's being pushed apart as it does. Now, another place we see this are in the rift valleys. Rift valleys are found in different parts of the world, but one place they're found is in eastern Africa. And so, like these lakes, like Lake Tanganyika and Lake Victoria, are examples of them, as are these. And basically, what's happening is the world is being pulled apart here by convection that is now starting to break a continent apart. And in fact, if you look up here, the Gulf of Arabia, this part here used to be connected to this part here, and then I forget, maybe 10 million years ago, volcanic activity like we see in these rift valleys started occurring here, and now I have 10 million year old rock here and 10 million year old rock here and very young rock here because I have a spreading center here because convection is causing this to spread apart. Another place we see this is the mid-ocean ridge of the North Atlantic ridge, as it's called, actually makes it to the surface here in Iceland. There's some speculation as to why Iceland is the only surface point where the mid-ocean ridge comes to the surface of there. Some people think that maybe it's a result of a asteroid impact in the past. We're not sure, but you can actually go to Iceland and look right at the mid-ocean ridge, which is kind of a cool thing. So, as I said, as the lithosphere pulls apart, all right, remember that's the upper crust, the crust in the upper mantle. As it pulls apart, a couple things are going to happen. One is there's going to be volcanic activity, but this volcanic activity there's not a lot of power to it. It's very gentle volcanic activity. You wouldn't even know about it if you were in the boat above it. But as we go down and explore it with submersibles, we see that there is volcanic activity occurring at different points along here almost constantly. Very, very, very low scale, gentle volcanic activity as this slowly pulls apart and the lava just fills in like squeezing toothpaste from below, like red hot toothpaste. All right, but what that does is this is new rock material, and as we move away from it, the rock material is older, and it's like a conveyor belt moving volcanic rock material away. All right, now in addition, what happens to just those gentle volcanic activity, we also get gentle earthquake activity. So in separating this apart, there's not a big buildup of pressure. We're just kind of pushing it apart with lava, but it starts to snap, and that makes this very small, low-scale earthquakes. And we often measure earthquakes using a scale called the Richter scale, where, for instance, a powerful earthquake would be 7, a devastating one would be 8, a few have been 9s, but these are typically 1s. They're very low-scale earthquakes. So if we look at a earthquake map of the world, which is something you could get exposed to or asked to interpret on the test, what we notice is the vast majority of the world's earthquakes happen along these mid-ocean ridges, and they're very small, low-scale earthquakes. We find a few of them in other places, but the vast majority of them occur along these mid-ocean ridges. We'll explain the other ones in a little bit, but just so you understand, this is a spreading center. New rock material is coming up here, and it's pushing the crust apart. And because it's a low area, it fills in with water, and we have oceans. So eventually, those rift valleys I was talking about over here, these rift valleys will eventually reach the ocean, and they're below sea level, and then water will come in here and fill it in and make a new ocean, basically. Okay. All right. Here's an earthquake map of Africa, and again, you can see, like in the Gulf of Arabia, I think that's what this is called. I'm not sure, but we see earthquake activity along the spreading center here, earthquake along the spreading centers here, along these lakes, and this is basically the African rift system. Now, there's other earthquakes too, but these are associated with spreading centers caused by a convection current reaching the surface. Now, as this material that comes up at the spreading center moves this way, it drags the crust with it, which basically opens this up and lets more magma come up. But it cools and it becomes more dense, and eventually it's going to sink back down at some point, at some distance away from the spreading center, because convection brings hot up, it brings cold down. And when the convection current sinks down, it drags the crust and the upper mantle, the lithosphere, with it. When it does that, the ocean crust gets deeper in regions we call a trench. So a trench is, in a sense, the opposite of a spreading center. Whereas a spreading center is where new rock material is coming to the surface and the plates are pulling apart. Here it's where the crustal material is sinking back down and carrying rock material into the earth to be remelted and basically recycled. So the regions where this sinking material happens, so we have basically somewhere out here we have a spreading center. It's cooling down here. The convection current is sinking down here. You don't need to know the word asthenosphere. Don't worry about it. But what happens is we call these regions here subduction zones, and these are regions where the material is being subducted, think like submarine, down into the earth, and it forms these trenches. These trenches can be quite low. They're the lowest places on Earth's surface, and they can go from basically a typical like 5,000-meter seafloor depth all the way down to like 11,000 meters. They're really, really deep areas. But the thing is, when you see a trench, you should be thinking rock is sinking down into the earth. Now, when the rock sinks down, what happens is it remelts, and what happens is as it remelts, it makes magma, which then moves up to the surface and erupts as volcanoes. So when we see an ocean trench on the subducting side of it, like above where the material is sinking into the mantle, we expect to see volcanic activity always. So I mean, that is just what you are going to see. So you won't find the volcanoes on this side of it because we're not sinking into the mantle here. We're sinking into the mantle where the crust is now past the trench and is now moving down, and then it melts, and then we get that earthquake activity. So when we look at Google Earth, we can see these trenches all over the place. And anywhere we see a trench, we should be thinking subduction. We have cooled rock material sinking back into the mantle, melting and making volcanoes. So let's just dive in a little bit and look at more detail on the type of volcanic and seismic activity we see here. So these subduction zones tend to have a lot of pressure in them, and when they release, they make very powerful earthquakes. So whereas the spreading center had very gentle earthquakes, they're just kind of pulling the earth apart. Here, we're building up pressure. The most powerful earthquakes in the world are associated with subduction zones. Japan, Alaska, places like that, the Andes, so the western part of South America. These are all subduction zones. Remember, if there's a subduction zone, you're going to see a trench. Now, we also associate volcanism with this too. So Japan is a volcanic island chain. Most island chains are volcanic, what we call island arcs. So they make this line of volcanoes a few hundred kilometers in the subducting side of the ocean trench. So we get, and now it's worth noting that that we get earthquakes along this boundary here. This is essentially a fault, and these earthquakes get deeper and deeper, and there's tend to be powerful earthquakes, and we also get melting and then for volcanic eruptions. Now, we have three different types of subduction that we can get. Well, three different types of convergent plate boundaries. So remember, when we pull them apart, that's a divergent boundary. When we push them together, that's called a convergent plate boundary. So one type of convergent plate boundary is an ocean-ocean. So ocean-ocean subduction zone, where ocean material is pushed below more ocean material, you get things like the Aleutian Islands that come off of Alaska. You get the Philippines. You get Japan. So these are what are known as island arcs associated with ocean-ocean subduction zones, which are convergent plate boundaries. Another type of convergent plate boundary is what we find, say, in my home state of Washington, or a better example would be along the coast of South America. And it's basically ocean continent subduction. Now, ocean continent subduction can lead to some very powerful volcanic activity. It's the most powerful volcanic activity because there's a lot of water that's caught up in this material that's being pushed down as it sinks, and that makes steam, and steam makes for explosive volcanoes. And so we don't get notice we don't get we have a trench, and we get volcanoes, again, a few hundred kilometers on the subduction side of the trench. But what we don't get here, I got a little better hurry up. What we don't get here is an island arc because it's in the continent. But we get the same pattern of increasingly deeper earthquakes and powerful volcanic activities when we have subduction at a convergent plate boundary. And what we notice is that these earthquakes, we can map them out, and we can see that the focus or foci gets deeper and deeper and deeper until it's so hot here that it's starting to flow past each other. It doesn't build up pressure anymore. So we're able to map out where these sinking pieces of lithosphere are by looking at these, basically following the fault line through the focuses of the earthquakes it produces. All right, so again, like I said, they form a few hundred kilometers away from the trench, and what we see is the earthquakes get deeper and deeper and deeper, and often are quite powerful. We get the rising lava here, and that is associated with powerful volcanic activity. Powerful because it has a lot of water in it. Uh, so here I have ocean convergence zone. So I have the Pacific plate here being pushed underneath. I'm not sure what the name of this plate is. Maybe the Japanese plate. I don't know. But here is what's known as an island arc. In this case, is the islands of Japan. They are volcanic islands. They have lots of earthquakes because this plate here is being pushed down this trench here. You go about 300 kilometers away, and you get a lot of earthquakes and volcanoes. Now, if we map out the Earth by looking at these earthquakes and volcanic activity maps, we see it's almost like you took a boiled egg and cracked the surface of it. Okay, so we get these what are called tectonic plates. They each of them have a name. There's not that many of them. I think there's like 14 of them, and each one is bounded on or usually I should say all of them usually are bounded on one side at least by a spreading center, a divergent plate boundary, and they usually will have a convergent plate boundary along them as well. So here I have a divergent boundary pushing the Nazca plate here, and then it subducts at a convergent plate boundary with South America. Uh, Let's see. In places where there are not at a plate boundary, we don't expect to find earthquakes. So, for instance, in the middle of the United States, we tend not to find earthquakes. Look at where Korea is. It's here. It's in the middle of the Eurasian plate. There's just not much earthquakes here. But you go to Japan, and there's a lot of earthquakes. Why? Well, because we have crustal material being subducted and building up pressure, making earthquakes as it slips underneath the islands. Here's a beautiful map of the world showing, I believe this is all the earthquakes. And what I want you to zoom in on is look at here. Red is shallow, orange is a little bit deeper, yellow is a little bit deeper, and green is the deepest. And so you can see where this crustal material is diving down, getting deeper and deeper and deeper. There's a trench here, and it gets deeper and deeper and deeper as we move this way. Same thing over here. And that's worth pointing out that the Himalayan mountain chain is basically what it was. It is a convergent plate boundary where the ocean material, it just simply all got subducted, and now you just have two continents pushing up against each other. It's really the only place in the world right now where we see that, but we still get some slippage down there, and there's still a lot of pressure here, and this is really being pushed by activity here of these spreading centers here pushing in that direction. Now, we have three types of plate boundaries. We have divergent, convergent, and transform. So we've talked about divergent, spreading centers, mid-ocean ridges and rift valleys. Convergent, basically where we have subduction happening, where we have trenches. And then we have transform. And transform is, there's a few places where we have side-to-side slippage. The most famous one of those is right here in California. Some of you might know going to school in Berkeley. You'll be right along a very, very famous fault line that extends basically from the Bay Area down to LA. It's called the San Andreas Fault, and it is an example of a transform plate boundary. Also, we find lots of these transform faults along here, but as far as plate boundaries, there's only a couple examples of transform plate boundaries, and the San Andreas Fault is one of them. So divergent plate boundaries, again, mid-ocean ridges, rift valleys, frequent mild volcanic activity, and shallow, weak earthquakes. Convergent plate boundaries we associate with ocean trenches. We associate them with island arcs or volcanic mountain chains. In the case of continental subduction, very explosive volcanoes, and deep, very powerful earthquakes. And so here's an ocean continent convergent plate boundary. And here is an example of the San Andreas Fault where we have a transform plate boundary. And I think that's all I need. Oh, okay, one last thing. We have symbols that you might be shown. So if you need symbols for it, here's what we do. We use parallel lines to represent divergent plate boundaries. We use this little tooth pattern to represent subduction at a convergent plate boundary. And the arrows point in the direction that the material is going down underneath the earth. And then we do these little half arrows that point us different directions here to represent, almost looks like electrons with different spins, that represent the side-to-side motion of a transform plate boundary. And I think that's all I've got for you. So sorry this was such a long one, but we'll get good at this.